Hi everyone, welcome to lecture 3 of synchrotron X-rays for micromechanical analysis. Before I get started, I just want to say I've had a few questions or a few requests for books or other references, and I'll try to send those out or put those online in a couple of days. And today's topics are the scattering vector, the Lowry diffraction condition, and rotating crystal diffraction experiments. So before I get started, I just want to do a little quick review just to make sure that we don't get confused as we go along today, because during the last 2 classes, I've been talking about a couple different types of basis vectors. We still have that problem between a coordinate transformation and a rotation. So very quickly, a coordinate system or coordinate system basis vectors are vectors which we can use to express tensor components we've got the crystal basis vectors, which are vectors which we can use to move or say describe positions in the crystal lattice. And integer combinations of these vectors are symmetrically equivalent positions. Similarly, we have the reciprocal lattice basis vectors. So these are constructed from the crystal lattice basis vectors. And similarly, allow us to describe symmetric positions in the reciprocal lattice. Coordinate transformation. Sometimes we're talking about as an orientation. It's just a set of angles between different coordinate system bases. And rotation is a tensor that changes the directions of line segments but not the magnitude. So this is what we've been working on the past two classes. This is what hopefully you took away. So today we're going to get serious about diffraction, and we're going to start moving a lot faster. Before we get started, we're going to make a few assumptions, which we're going to be using throughout the day, that's going to help us derive the diffraction condition. First is that we can model X-rays as plane waves. To the direction of propagation of all X-rays to and from the sample are equivalent. So what do I mean by that? So I'm going to try something new right now. I think my drawing skills are going to fall apart at this point in the class. So I'm going to switch over to some figures that I've drawn. So what we see here is that from our source point to our sample and then to the detector or our observation point, as this distance gets bigger and bigger, all X-rays from the source to the sample have close directions. So we're going to assume that there's, even if we've hit slightly different points on the sample from a single source point, we're going to assume that all these directions are the same. And then from X-rays emitted from different points on the sample to our single detection point, we're going to assume that these are all equivalent. And so more formally, if these distances are much larger than the wavelength, which is actually a fairly small distance since the wavelength of X-rays is so small, then we can assume that these propagation directions to and from the sample are equivalent. Three, the interaction of X-rays with the sample is weak. What I mean by that is that the wavelength and direction of propagation of X-rays doesn't change in the sample, or as it enters the sample. This is something that you have to worry about a lot when you're dealing with optical light. And our last assumption is that interactions of incoming and diffracted X-rays is weak. So we don't get things like standing waves in the crystal. So this is good for most metal samples, crystals that have defects in them. This is not true if you have something like a large single crystal of silicon. So today, to start off with, we'll be treating X-rays as a plane wave. The general form of a plane wave is an amplitude times a cosine or a sine. And then we have a wave vector dotted with the current position. Minus a frequency term plus a phase shift. What we're going to find today is that it's a lot easier to deal with waves in their complex form. And what we're going to remember is that the actual wave is only the real part, but we'll be operating on the complex form. And so the complex form of the wave is exponential e to the imaginary I so that's that phase shift. So just going over again, this is our wave vector. This new here, this is the frequency. This t is the current time, and this phi here is the phase shift. Well, so today we're gonna be looking at interference of X-rays. And what we're gonna find is that the interference between X-rays of different frequency or wavelength, they're coupled together, tends to average out very quickly to zero over very short amounts of time. So we're mostly going to be neglecting this term today. And as a reminder, the wave vector k is equal to 2 pi over lambda. So this is the magnitude of the wave vector times the direction. And this k hat is the direction of propagation. So now we're going to talk about interference. And phase shifts. So do the superposition principle. EM waves, like X-rays, interfere with each other. I mean that we can add them up. So adding together two waves is an example. With the second wave being phase shifted from the first. We find that the sum wave has the form 1 the amplitude plus 1 plus this phase shift term times just the form of a general plane wave. So what we see here is if we add together two waves with the same wavelength and wave vector, but they're just phase shifted from each other, all adding together this phase shifted was added this phase shift term, which can range from 0 to 2, with 2 being fully constructive interference, and the amplitude goes up, or fully destructive interference, and the amplitude is 0. So our goal today with the diffraction condition is try to find the condition in which we can orient the crystal in such a way that the X-rays that are emitted from every single atom all constructively interfere with each other to boost the amplitude of this plane wave. So now I'm going to show a quick figure where we're going to talk about observation points and phase shifts. So what we have here is a traveling plane wave, and we've got two observation points, 1 and 2. The apparent phase shift is related to the change in path length along the direction of propagation of the X-rays. So this change in path length is equal to K, or K hat, times this vector between the two. And note that I've, just be careful with signs here, I've drawn the vector from 2 to 1 in this class. So it can go either way, but you just have to pick one and be consistent. So our phase shift between the 2 points is 2 pi over lambda times delta p. This is the path length difference. You remember last week, this is something that we talked about in Bragg's law, which is equal to 2 pi over lambda times k hat minus delta x. So remember, this is with the vector from 2 to 1. This is equal to minus k, our wave vector, times delta x. So bring it all together. We'll be using this a lot today. The phase shifts of observation between 2 points, phi, is equal to minus the wave vector k times the vector between the 2 points. And that brings us to the scattering vector. The question is, what is the phase shift of waves emitted by 2 points here, which are generated from a single source? So again, I have another picture. What do I mean here? So in this picture, we've got a single wavelength that stimulates a secondary wave from these electrons here. We'll have these be electrons, these points. And then what's the phase shift between the stimulated waves that we see from these two electrons? So we're going to add together the two waves and the amplitudes of the waves. So total amplitude that we observe from point 1 is this outgoing wave vector times the position of electron 1 plus the amplitude of waves of the wave emitted from the second electron. Plus a phase shift. What we're going to assume is that we're far away from these two electrons. So we'll find that this term here is about equal to delta x, or is about equal to x. So that the distance between the two electrons is small compared to their positions in space. But then the question is, what is this phase shift here between the two? So this total phase shift is a combination of a phase shift between the observation of the two incoming plane waves and their difference in path length in the outgoing direction too. So we talked about the incoming plane waves passing by the two observation points, which is the two positions. So that's the two electrons. Be careful about minus signs here. So the incoming phase shift, the incoming wave vector, dotted with the position difference. And what we find if we look at that drawing is that the outgoing phase shift equal to the outgoing wave vector dotted with the position shift. And see, let's make sure to really pay attention to that minus sign here. So this means our total phase shift is equal to the difference between the incoming and outgoing wave vectors dotted with the position difference between the two. And this vector here is important. We call this the scattering vector. Q. Sometimes this is also referred to as the momentum transfer. And when that gives us our total scattering amplitude emitted from those two electrons, so this is important. Our phase shift between the two is just the scattering vector dotted with the difference in position between the second electron and the first. And we can generalize this. We have more than one electron. Amplitude total A times 1 plus some J1 times the number of electrons minus 1 that fall off. So this here is just the scattering vector times, or dotted with the position shift of the current electron, delta xj. So we can calculate the total scattering amplitude that we'd observe from any collection of atoms if we know all their positions in space with relative to a reference electron. So I'm going to generalize this really quickly to the scattering of a, instead of from points, from a charged density. So the infinitesimal scattering from a piece of an atom equal to the scattering amplitude times the charge density times an infinitesimal volume. What we can do is we can integrate this term. So we can integrate over the charge density of an atom. So the charge density at a position relative to a reference point times the scattering vector times the position of that charge density times the volume element. And what this term is called the atomic scattering factor. So all this is the integrated scattering amplitude from the charge density that makes up an atom. This value, this atomic scattering factor, can be found in X-ray tables. This can be calculated, but it's often something that we measure. Okay, so we've been building up. So we've done scattering amplitudes from electrons. Done electrons, I just did an atom. And remember, the most important thing, the only thing we were really doing, but don't get too worked up about it, is we were just calculating phase shifts. That's it. We're just calculating phase shifts. And the phase shift between 2 points is our scattering vector Q, dotted with the position between those 2 points. That's it. So since we've gotten good at calculating these phase shifts, let's talk about the scattering amplitude from a whole crystal. And I guess we don't even have to start a crystal, from a collection of atoms. So our total scattering amplitude equal to A times the sum, n equals 1, to n, which is the number of atoms, times our atomic scattering factor times the phase shift between the atom positions. So let's take a pause right here, looking at this equation. We're going to be talking about this equation for a good part of the rest of the day. But what's important to remember is this is it. We're done here. If you want to calculate the scattering power from a collection of atoms, this is all you need. You can calculate it here. And so while this was a problem when they were first developing these things like, or trying to figure out the diffraction condition, these days we have computer programs where things like molecular dynamics will tell you the position of every single atom in an amorphous volume, in a crystal. If you know this, you can directly calculate the scattering amplitude. So you don't have to make any assumptions here. And so what I really want to emphasize is don't limit yourself to things like analytical solutions that have been calculated in the past. If you want to know what the scattering power is from a crystal, let's say a dislocation in it and a defect in it, all you have to do is program in those positions that we know of where atoms sit in a dislocation and calculate the scattering amplitude yourself. This is something that can be pretty easily programmed into a computer. But now we're going to go a little bit farther. So I'm going to leave this up top. So if we have a crystal, we know something about the position of the atoms. We can relate those to different parts of the unit cell, and we know that these things repeat periodically in space. So what we're going to do is we're going to break apart these relative positions of the atoms into this big X plus this small c. So this is the position of the unit cell. And the c is the position within the unit cell. We know that we can describe our unit cell positions as linear combinations of our crystal or direct lattice basis vectors. U times A1 plus B C2 plus W times B3. So we'll use this in a second. And then we can break apart our total scattering amplitude into, so big N right here. Number of cells, double summation, number of atoms in a cell. So all I've done is break up the sum of atoms. We're going to sum over the atoms in a unit cell and then repeat over the unit cells. We can break apart those two summations. So I've broken apart this equation because I know that this is a crystal and it's periodic. And I want to look at this term here. We look at this term here, we can see that this value can range from -1 to 1. This term right here. But if we want this to constructively interfere, we want this value to always be equal to 1. And for that to occur, scattering vector dotted with the unit cell position must be equal to an integer multiple of 2 pi. So this must occur for fully constructive interference of all the unit cells. Now, what's nice by construction is the only time that this occurs is when the scattering vector is equal to a reciprocal lattice vector, which we remember from last class was H B1 plus K B2 plus L E3. Because remember that AI with BJ is 2 pi times the corner per delta by construction. And we see that when we multiply a reciprocal lattice vector, we dot it with the unit cell position x, we get 2 pi times HU plus KV plus LW. Which is an integer. So that's it. That is the Lowry diffraction condition. If the scattering vector is equal to a reciprocal lattice vector, diffraction occurs. So hopefully there wasn't too much to that. All we did was we built up the diffraction condition from a set of phase shifts between all the atoms in our crystal, or all the unit cells in our crystal. So I want to go back to this term here. So that term of the scattering of the atoms in a unit cell. And what this term here is referred to is the unit cell structure factor. Again, it's just calculating a set of phase shifts, what we've been doing all day. Well, what's important is that sometimes, so the scattering power reflection is proportional to this unit cell structure factor, but occasionally the structure factor can be equal to 0. When that's the case, when the unit cell structure factor is equal to 0, we call that a forbidden reflection. So all you have to do to calculate if a forbidden reflection, or if a reflection is forbidden, is just replace these Q's with this reciprocal lattice vector calculate away. Now I want to talk about Ewald sphere. What I haven't talked about today much is that scattering that we're talking about today in diffraction processes is elastic. And what I mean by that is there's no energy change. During scattering. Which also means that there's no wavelength change. So if there's no wavelength change between the incoming and outgoing diffracted beams, the magnitude of the incoming wave vector has to be equal to wavelength of the outgoing or diffracted wave vector. What this means is that there's a restricted set of allowed scattering vectors for a fixed incoming wave vector. And what was found was that all the allowed scattering vectors that maintain the equivalent magnitude of the incoming and outgoing wave vectors fall on a sphere. Which is Ewald's sphere. Ewald sphere is a powerful graphic construction that can help you visualize the diffraction condition. I'm going to pull up a figure in a second, but I want to emphasize that being able to think about diffraction in terms of Ewald sphere in reciprocal space and reciprocal lattice will help you be able to really visualize diffraction and be able to predict where diffraction peaks will occur without necessarily having to do all the math. That you could do a pretty good job of figuring out where diffraction peak will show up in space. So let me pull up a example. So what we have here is, here's a picture of Ewald sphere. So we have our incoming wave vector, and then what we can see is that all outgoing wave vectors must have the same magnitude of the incoming one. So all possible outgoing wave vectors must lie along this sphere here if k out is centered on this spot. And we can see that all scattering vectors, q in reciprocal space, must lie on this sphere. And it's just a consequence of the magnitudes of the incoming and possible outgoing wave vectors being equivalent. And so here's an example of, I've got a set of reciprocal lattice points, and this sphere is all possible values of q. And we can see that the reciprocal lattice vectors are not making contact with the sphere, and therefore diffraction is not occurring. So this is just a graphical picture of the diffraction condition. So now here is a picture of the diffraction condition when diffraction is occurring. A reciprocal lattice vector is on Ewald sphere, which is equivalent to an allowed scattering vector. And we can see that the corresponding outgoing wave vector, centered at the same point as the incoming wave vector, also touches this reciprocal lattice point. So k in plus q equals k out, or just equivalently k out minus k in is equal to g, which is equal to our scattering vector here. So this takes a little bit or a lot of bit of thinking, but it can be very, very powerful if you can start to visualize this in your head. So we're almost done for today. The last bit I want to talk about today are rotating crystal diffraction experiments. So what have we figured out today? So we figured out that diffraction occurs when the scattering vector is equal to a reciprocal lattice vector, and that the magnitude of incoming and outgoing wave vectors are equivalent. So now what we're going to do is we're going to combine these two, and we're going to use these two sets of equations here to try to solve and figure out when diffraction occurs when a crystal is rotating about a fixed axis. Let's start with our relationship between the magnitudes of the incoming and outgoing wave vectors. We can change K out to reflect the relationship between the incoming wave vector K out and the scattering vector. And now we can plug in our diffraction condition. So this here is a scalar equation. And what we're going to do now is we're going to use all our coordinate transformation machinery that we've been working on the past 2 lectures to try to figure out how a reciprocal lattice vector must be oriented in order for this equation to be satisfied, which also satisfies our Lowry diffraction condition. Now be careful about which coordinate system that we're working in. So I'm going to say that we're working in the lab coordinate system. So we're going to be talking about components Kane in the lab frame. Plus a reciprocal lattice vector in the lab frame. This is what we don't know. We don't know how we have to orient a reciprocal lattice vector in the lab frame. But what we usually might know or want to find out is the orientation of this reciprocal lattice vector with respect to the sample. We're going to use our transformation matrices. And still, we might not necessarily know what the orientation is of the reciprocal lattice vector in the sample frame either. But if we know the crystal orientation, we can figure that out. So remember, this was a special transformation that we called the crystal orientation. So we're going to assume that we know this crystal value, this value here. So we know which way lattice planes are oriented with respect to our crystal, which is sitting there on the table. So in a rotating crystal experiment, we're rotating about one fixed axis t by an angle omega. Usually, t is perpendicular to our incoming wave vector. Just to write things out explicitly in our equation here, this transformation from lab to sample is a function of how the sample has been rotated about t by this angle omega. Times our orientation, times our reciprocal lattice vector, so this plane of interest. And so our big question here is, how do we solve this? This is a transcendental equation. It's not a particularly easy equation to solve. And what we'll find is that this equation here has 0, 1, or 2 solutions. And that's easiest to see with our Ewald sphere construction. Is there a problem?
The previous step, you might have written crystal instead of sample.
Or sample instead of crystal with your G vector.
Ah, sorry. Yes.
I also had a question. So before, when we were using the like superscripts, when we were going like lab to sample frame,
yep,
they would have been the other way around. so that the transformation would have been close. So the superscript transformation numbers or letters would have been closer to the transformation matrices. Is there a reason it's different here?
So they are closer.
closer.
They are closer. CC,
Yeah.
SS, they match up there, right?
Yeah.
Yeah, so that's.
They should match. That will be the right way.
Right.
Yeah.
So look, so we're going to use our E-wall sphere construction to demonstrate how there can be 0, 1, or 2 solutions. So I've drawn E-walled sphere here, and I've drawn 3 reciprocal lattice vectors in space, which are lying here on this plane that I've drawn with a dotted line. So this is a side view, and we're going to be rotating about this vertical axis by the angle omega. And so if we look down in the top-down view of the 3, so this is a cross-section of E-walled sphere. So we know that diffraction occurs when the reciprocal lattice vector hits E-walled sphere. We can see that this G1 here, as it rotates, will never hit E-walled sphere. So diffraction won't occur. And so this is if you plugged in this reciprocal lattice vector, you get 0 solutions. There's also this one edge case, G2, where as you're rotating around, you just nick the edge of E-walled sphere, and then you have one single solution. What you can also have is this G3 out here, and as this rotates, this will hit E-walled sphere twice. So in reality, this edge case does not happen very often. You'd have to be pretty lucky to orient your crystal this way. But in reality, most reciprocal lattice vectors will either, in a rotating crystal diffraction experiment, will either not diffract, or they'll diffract twice as they're spinning around 360 degrees. So as we can see, this is pretty helpful for trying to just figure out solutions without necessarily having to solve the complicated equation that I just have written up on the board. But if we want to solve this equation, one possible strategy is to recast it as a minimization problem. So we've got a scalar equation and one scalar value that we're looking for. So we can recast our function. We can throw an absolute value in here. And we'll want to minimize the magnitude of our incoming wave vector. So if we reformulate the equation this way, so it's tough to see with all our bars, but this is all an absolute value. And then we could plug this equation into a computer minimization, a numerical minimization, and be able to solve this no problem to find the omega values because the minimum points here are at 0. However, this equation also has an analytic solution. what we can do is we can square both sides of the equation. We can solve it. And I've actually worked out the solution for, so remember, this solution that I've worked out here is if the incoming wave vector is traveling in the minus e hat 3 direction in our lab frame. And our rotation axis of the sample T is parallel to the e hat 2 direction in the lab frame. So if we work things out, we get cos omega times the third component of G. I've dropped the HKL just to keep things a little less busy. In a sample frame minus sine omega 1 sample frame equals lambda or pi. And if we define, and I just like to note that this is an exercise that you might want to do once in your life, but then never again. So I'm going to define a variable y equals lambda magnitude squared over 4 pi. Skipping through 2 steps, but just to show this in a final form, or in an informative form, we get minus square So I have to continue on here. Like I said, you only want to do this once. And what you'll notice, if you're a lot sharper than me, is that this is actually a quadratic equation. Where A is minus G1S squared plus B minus 2 G1 S Y C G3S squared minus Y squared, which gives us, for our solution for omega, yes.
So it looks like someone asked in the transcendental equation, is the GHKL in the crystal coordinate system?
So what I've been working in is so did you see the S at the top of the values? So I've just assumed that you know the crystal orientation and that you've transformed the reciprocal lattice vectors into the sample frame, if that's helpful. So we know that, so I'm not carrying around that extra A transformation matrix that transforms us from crystal to sample. So you would do that right at the beginning of the calculation and then just start working with the sample, the components in the sample frame. So again, it's just a quadratic equation. So this is the value for our angle omega. But what's important to notice is that this arc sine has two solutions between minus pi and pi, and that this quadratic equation here, or this part of the equation also has two solutions. So there's 4 solutions total here. And that arises from that trick that we did in the beginning where we squared both sides of the equation. But when we physically looked at Ewald's sphere, we saw that there are only 2 real solutions possible. So what that means is when you do this calculation here, you have to find all 4 solutions and then check them against what you know to be true. So you still have to make sure that the magnitude of the incoming and outgoing wave vectors are equal. The 2 false solutions won't be able to satisfy this elastic scattering requirement. So now, so you know omega. So you know how G must be oriented in the lab frame. And you know the wave vector of the diffracted beam in the lab frame. So this is it. You're done. And the reason we've slogged through this is because this calculation here is at the heart of all the high energy diffraction microscopy methods that are used today for figuring out things like orientations of crystals or figuring out complete orientation maps in 3D. This is just done lots of times, very, very fast. But if you can understand what's being done here, you can understand what's at the core of these codes. It's just calculating the diffraction condition lots of times. And later on in the course, we're going to be talking about methods for solving inverse methods of this problem, but really it's just kind of tweaks of that rotating crystal problem that we just worked through. So next week, polychromatic X-ray diffraction. So instead of having the problem where we have a single monochromatic wavelength hitting the sample and trying to figure out how we need to rotate the crystal for diffraction to occur, instead, what happens when we bathe the sample in an X-ray beam that has lots of wavelengths in it? And then the question is, what energy or what wavelength will the crystal diffract? Then we'll also be talking about diffraction from polycrystals. Thank you for listening.